Very good. I'm going to continue now with with this topic, and we've gotten up to contrast. Definition of contrast is the degree of difference between light and dark areas on a radiograph. And contrast is quantified by the window width. Remember, we have two terms, window level and window width. Window width is the gray sections of the radiograph. That is not the brightness and the darkness. This light and dark, that is window level. And so my analogy, I'm sure you've heard it before, opening a window will allow more light into the room, and allowing more light into the room makes it lighter or darker. Opening a sliding glass door a little bit will start to show us some of the colors and some of the grays, but if we open that sliding glass door more, well, we're able to see a lot more individual gray shades. And so contrast is window width. Contrast resolution, the ability of a digital imaging system to display subtle changes in the shades of gray. And contrast resolution is directly related to the bit depth of the pixels in the image. I talked at some great length about bit depth yesterday in my recording, having to do with 2 to an exponential power, and the intent being that a pixel has the ability to record thousands and thousands of individual numbers representative of how much exposure that pixel got. And so we can limit that number of grays by the pixel bit depth that we will allow. And typically that is written into the lookup table, which tells the software, when we do the histogram analysis, tells the software how many grayscale we want for this particular image. So contrast resolution in digital imaging directly related to bit depth of the pixels on the image. That being said, higher kV and lower MAS values can be used in digital imaging, lowering the patient dose without affecting the image contrast, as this technical change did in the film screen radiography. Back in the film screen days, kV was our primary controller of contrast. In the digital environment, the primary controller of contrast is the lookup table. So we can use correspondingly higher kV, and the benefit of that is less MAS based on the inverse square law. However, when we turn our kV up, scatter control is more important, since digital image receptors are more sensitive and have greater latitude. Even a small amount of scatter radiation is going to detract from the image. And as you remember from physics, when we increase the kV, we increase the presence of scatter radiation. So there's such a thing as too much of a good thing. Resolution considerations. I don't know if this will be on your certification exam or not, but heads up, there's something called low contrast resolution, the ability to capture and display subtle energy differences in the area of interest. And these are what are responsible for low energy shades of gray on an image. Practical application of that: you have a child, and if that child is wearing a diaper, that diaper will show up, especially if it's a wet diaper. That will show up as an artifact based on the fact that digital imaging is so sensitive to low contrast resolution. Another consideration for resolution is temporal resolution. Temporal resolution is easier to control. Temporal resolution is a function of exposure time and motion of the body part. This is typically controlled by good, clear breathing instructions and asking the patient to hold very still. We can also accentuate that by using extremely short exposure times to optimize temporal resolution. Resolution in general, the overall clarity of the image. This is a term that we use, spatial resolution, the ability to image small objects that have high subject contrast. And the example that I use for this is the trabecular pattern of bone, okay, which are very small objects, and they have a certain high subject contrast. How can we get good spatial resolution as a general rule? Well, let's not overlook the geometric properties. Spatial resolution, one of the things we need to consider is that good detail exists even if it cannot be seen. If there's something that's overshadowing or masking the spatial resolution, then that's distortion, or that may be fog, or that may be a whole variety of different things. And if we can, remember what we talked about, if we can limit the geometric unsharpness and control the unsharpness, then we are able to get that much better a radiograph. So, spatial resolution is the degree of geometric unsharpness, or sharpness, if you will. The art of radiography is controlling the degree of unsharpness so it does not interfere with the diagnosis. And there's several ways that we can go about doing that, which I'm going to talk about here in a moment. Spatial resolution is also referred to by definition, by sharpness, by recorded detail, or simply detail, although these terms, I think they harken back to the film screen model. The popular term now in our current digital imaging model, we use the term spatial resolution, and that's going to be the term that you will see on your certification exam. Digital imaging systems spatial resolution is dependent on the pixel size. I think in my video yesterday I talked about if you have smaller pixels, then you have better spatial resolution. And each pixel is a two-dimensional data point, individual pixels. Remember, there's millions of pixels on the matrix. If we have larger pixels, well, there aren't as many millions there, and if they're larger, we don't have as good a spatial resolution. If the pixel sizes are smaller, then we have better spatial resolution. Additionally, the greater the matrix size for a field of view, the better the spatial resolution will be as well. And so what we have here, this is an illustration of a matrix, 1, 2, 3, 4 columns and 4 rows. And so each of these represent an individual pixel. And when the X-ray beam comes down through the patient and interacts with the image receptor and interacts with the pixels, the pixel will record a certain value based on how much radiation it received. Okay, and each of these individual pixels then keeps that particular reading, and then those are sequentially read out at the point when we do histogram analysis, at the point where the data is sent through the software program to process the image. Okay? Incidentally, the pixel, the individual pixel at location row 3, column 4, is a two-dimensional data point. But when you look at row 4, column 4, and we add depth to the pixel, then it becomes a term called a voxel. I don't think that will be on your certification exam, but it is something of interest. All right, so how does this play into recorded detail? And the answer is that here I have 4 of the same image, but can you appreciate how the first one is probably the best? And that's probably based on the fact that we had a larger image matrix with smaller individual pixels to make up all of that spatial resolution. The second one on the top row, well, that's also not bad, but perhaps we had the same number of pixels, but on a smaller image matrix. And then the third and the fourth one, you can see how as we get fewer and fewer pixels, larger and larger pixels, smaller and smaller matrix size, how the image suffers. So here's kind of how it works. I'm looking at the illustration on the left, and these are individual pixels, and these pixels have captured a certain level of radiation exposure, numbered an arbitrary number of 10 on all four corners, and in the center, an arbitrary number of 2 in the center on the upper and lower row, an arbitrary number of 6 in the center on the first and fourth column. And looking at the grayscale image next to it, can you see that all of the 10s are the same grayscale? All of the 2s and all of the 6s are the same grayscale, corresponding with one another. And so these are the values that would be uploaded during the image processing portion of the digital image. And this is what combines to give us the final resultant image. Okay, so image processing system limits recorded detail. It's dependent on the acquisition size, the pixel size, and the display matrix. It is also dependent on the grayscale bit depth. The grayscale bit depth, remember, is that each pixel is capable of representing a wide range of different shades of gray, ranging from total black to blinding white. And that number of gray shades, which can be captured, is determined by the grayscale bit depth and expressed exponentially. If you took out your calculator and you calculated 2 to the 8th power, you would come up with 256. So 2 to the 8th is 256 individual shades of gray that we can put in between total cave darkness to blinding surface of the sun whiteness. If you're unfamiliar with your calculator function, well, you can take a piece of paper and you can multiply 2 times 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 2, and you should come up with 256. Same thing is true with 2 to the 16th, which will be 65,536 shades of gray. Don't do that longhand. Just trust me, it works. Assessing recorded detail, we can use a resolution test tool. And I talked about this in a video yesterday as well. A resolution test tool has line pairs. Remember, a line pair is a dark line and a white interspace. And so it's the line and the interspace, and that becomes a line pair. And you can see that they're smaller and smaller and smaller, representing more line pairs per millimeter. Up here is 1 line pair per millimeter. Down here is 2 line pairs per millimeter. Can still sort of see it, not as clearly, but then when we get down to 4 and 5 line pairs per millimeter, well, it becomes very difficult to see. So, line pairs per millimeter is one of the ways that we can assess spatial resolution. And if we're having difficulty seeing those line pairs per millimeter, despite the fact that we may be able to hold that line resolution test tool pattern in our hand and look at it and see line pairs per millimeter all the way out to 5 line pairs per millimeter, but can our radiograph demonstrate the same thing with the same level of clarity that we can see it with our eyes? To the extent that we can, that measures the modulation transfer function of our radiographic image. All right, let's move forward here. All right. Spatial resolution, the ability of an imaging system to accurately display objects in 2 dimensions. And there's 2 terms here that you should be aware of, penumbra and umbra. I want to take a look at illustration A here. And illustration A is that the object that we're radiographing is exactly the same shape as the divergent beam emanating from the X-ray tube. And so inasmuch as the edges of this object are exactly in line with the divergent beam, then we're not going to have any edge gradients there. We're going to have a very clean, clear border, and so that is going to show up as the umbra. The umbra is the shadow of the exposure from our radiation. Now I want to compare image A with image B. With image B, our object is not the same shape as our divergent beam, but our X-ray beam comes through the object, and at the periphery of the object, it has varying levels of penetration. And so this unsharp edge gradient, perhaps up here, is reflected not as the umbra of the object, but the border of unsharpness of the object, and that's called penumbra. Okay? So we have umbra is the shadow, the penumbra is the unsharp edges of it. Take a look at C. C is a round object, and with regard to a round object, we don't have any concrete solid edges. And so we have quite a bit of penumbra and not as much of the umbra image. Why is this important? The structures that we take pictures of in the human body are not necessarily like image A. They do not fit the shape of our exit beam, of our central ray. And so as a result, there is always going to be some level of penumbra on our radiographic images. Distortion. We have distortion from the perspective of shape and size, and that is typically caused by unequal magnification of different portions of the same object. Here is, there's a couple of different ways that this works. One of the ways that we can eliminate it or control it is with SID and OID, and I'm pretty sure that we did a lab about this. As you recall, source to image receptor distance is a major factor for magnification. Longer source to image receptor distance yields less magnification, based on the fact that if we move our source back, then we can collimate our beam and we can use only the straighter X-rays, as opposed to when we move in, we have to open the beam up a little bit. Look at my head as I move further back and further forward. So if I had a certain X-ray beam down here, I would have to collimate this wide. But this wide, when I come forward, is not going to be enough. So I need to open my collimator up a little bit. So SID is a major factor for magnification. I think that the time is coming when we will see 40 inches, which is standard SID now, is probably going to be increased across the board to 44 or to 48 inches. And I think that that will happen during your career, probably early in your career. The corollary to SID is object image receptor distance. And so we want to try to keep our object as close to the image receptor as possible to decrease magnification. OID should be minimized whenever possible to minimize magnification and improve resolution. All right, I think I'm going to stop here for a second and see you back in another moment.